All right, on this page, we're going to start talking about rotational energy. When we talk about rotational energy, we get to go back to LOL charts. So we have to think about those things like gravitational potential energy. That formula, remember, is mgh or mgy, depending on how you want to see that, h or y. Then we have translational kinetic energy, which is from before. We know this from before is 1/2 mv squared. But now we also have rotational kinetic energy. And that equation is just going to take, it's a parallel equation. The 1/2 and the 1/2. The mass, we call that inertial momentum. And then the velocity, we would call that angular velocity. I had a hard time getting a font to do that. That's your angular velocity, not just a regular W. Okay, so if we have a bowling ball with a certain radius and it slides down the ramp, then how fast is it going to be at the bottom of the ramp? Well, this would be like an icy ramp. Something, I don't know, you coated it with Vaseline or something and it's just sliding down rather than rolling. And maybe you've even been to a bowling alley, you know that they do grease those alleys. And sometimes you will, if you watch the ball, it will slide rather than roll. But anyway, we need to calculate the linear velocity. Well, if we're talking about linear velocity and we're talking about it just sliding, then we're just going to stick with the old-fashioned gravitational potential is going to be turned into the linear or the translational, call that translational. And so we're going to have mgh equal to 1/2 mv squared. And when we were in this unit, we then kind of rearranged this because we're looking for velocity. And so we said, well, the masses will cancel. I'm looking for velocity. I'm going to multiply by 2. So I'm going to get 2gh is equal to v squared. So in other words, the square root of 2gh is equal to the velocity. And so that's what we're looking for now is that linear velocity. And so it is 2 times g times the height, which is in this case 2 meters. And we just take the square root of that. So we're going to put that into our calculator and see what we get there. And so we put that into our calculator and we get that the velocity is 6.26 meters per second. That's how fast it's going if it just slides. It doesn't roll. Well, what happens if it rolls? Because typically a ball is going to roll. Well, we're going to use a similar setup. Now, all this goes back to the LOL charts, that we have this potential energy, this potential gravitational energy, and it has to be transferred because it's going to move, and when it moves, it gets transferred into different kinds of energies. So it will change some of it over to translational, but it will also turn some of it into rotational. So it doesn't all go into translational, some of it's turning into rotational as well. Now, I'm going to go ahead and set up my equation that my mgh is equal to 1/2 mv squared plus 1/2 I times omega squared. I'm going to substitute even further because the I, because this is a ball or a sphere, the I is 2/5 mr squared. And so I wrote that over here in the margin for you to remember. Again, you don't have to memorize it. It should be given to you. But I'm going to go ahead and plug that in for my I, and my my rotational velocity is velocity over radius, so I'm going to plug that in to my omega. And so I have mgh equals 1/2 mv squared plus 1/2 times, now I plug this in, 2/5 mr squared, and for my linear velocity, or my angular velocity changing over to linear is v over r, and that gets squared. And so now I'm going to look at, well, what can I cancel to make my life a little bit easier? There is an m in all of it, so the masses will cancel. Then this r squared and this r squared will also cancel each other out. So let's see what we're down to. We have a gh over here on the left. We have a 1/2 v squared, and we have, now this 2 and this 2 are going to cancel, so we have a 1/5, and that's all canceled out, and we have another v squared. Well, we have like terms, so we can add these like terms, and if you know how to add fractions, we are going to add those fractions together, and that's going to add up to 7/10 v squared. And so we have gh is equal to 7/10 v squared. We're looking for its linear velocity, that's v. So I'm going to come up here, I'm going to multiply both sides by 10 over 7. and I'm going to take the square root, and that's going to be my velocity. So now I just have to plug in g and h, which is 2 meters, to find my velocity. And my linear velocity at this point is 5.29 meters per second. Now, keep in mind that is linear velocity. That's not how fast it's spinning, it's how fast it's getting down the ramp, okay? 5C, in which situation sliding or rolling results in a higher velocity and why? Well, let's look at our two calculations. The first one, where it was sliding, had a higher velocity. So sliding, and the reason is because all the potential energy is converted into linear velocity. When it rolls, some of the energy goes into rotating the ball. And so kind of back up to this diagram here, in the first case, it's just sliding. So all that energy goes into sliding. Whereas in the second case, we have this rolling. And we can see, if you're losing some of that, because that's not going to go as fast as the one that's going straight down. And the reason is because all that energy gets converted into linear, whereas in the other one, some of the energy goes into rotating as well. All right, next example, number 6. Two disks, both have the same mass and the same radius, are released from rest at the top of a ramp that makes a 37-degree angle to the ground. At this point, I'll tell you that we don't really care about that angle. That is just a distractor at this point. The disks are identical in mass and radius, but one is a solid disk, so it's 1/2 mr squared, while the other one is hollow. In other words, it's a rim, a cylinder. Just a rim is a good picture. What are the two disks' linear speeds when they reach the bottom of the ramp? And then which is faster and why? Okay, so this is going to get into comparing these linear momentums between the different shapes. If we watched the crash course, she talked a little bit about that in that video. And so what we need to do is we need to compare the solid disk and the hollow cylinder. So I've come out here because I'm going to run out of space if I don't. But for each of these, I'm going to take the gravitational potential is equal to the linear and the rotational. Same thing here. Our next step is also going to be the same. That is, gravitational potential is mgh or mgy, however you want to say that. Linear is 1/2 mv squared. Rotational is the same thing. That's a W, but it should be an omega. I just don't have that font, so that's omega. And now we are going to be plugging some of these in. So that's where it's going to separate and become a little bit different, is that the solid disk is going to use this 1/2 mr squared, whereas the cylinder, or the rim, is going to use the 1/2 mr, or excuse me, just the regular mr squared. So let's go ahead and start plugging some of those in and seeing how we can simplify these equations. Okay, so I'm going to plug in, I know it's kind of messy over here. mgh is equal to 1/2 mv squared plus 1/2. Now I'm going to plug in my I, which is 1/2 mr squared. And for my omega, I am going to plug in my v over r squared. Well, v over r, and I square that. And so now I'm ready to start looking at what cancels. So once again, there's a mass in everything. This r squared can cancel with this r squared. And so what I'm left with after I cancel everything out is a GH is equal to 1/2 v squared plus, now I have a 1/2 and 1/2, that's a 1/4 v squared. And so in other words, GH is equal to 3/4 v squared. And what I really want is to solve for v. So I'm going to multiply both sides by 4 over 3. And then I want to take the square root because I have a squared. And that's going to be my v. So now I'm ready to plug in. So I have my g, which is 9.8, and my height is the height of the ramp. And the ramp is 1.5 meters, so that's my height. So I can plug that in and then do my calculation. So I'm going to plug this into my calculator, take the square root, and I get my velocity from there. And so I get 4.4 meters per second. That's my linear velocity for the solid disk. I'm going to go through the same process for my cylinder. That is, I have my mgh, I have my 1/2 mv squared. I'm going to plug in the I for this equation into that I. And for the omega, I'm going to plug in my v over r. So I have my mgh is equal to 1/2 mv squared plus 1/2, and then my I in this case is just mr squared. And my omega, once again, is v over r, and I need to square that. So now I'm going to look for what cancels. Everything has an m, so I'm going to cancel that. This r squared cancels with this r squared. And so again, at the end of all of that canceling, I have GH is equal to 1/2 v squared plus, now this time I just have a 1/2. I don't have another fraction, so it's just 1/2, and I have another v squared. In other words, GH is equal to a half plus a half is a whole, v squared. So velocity is the square root of GH in this case. So I'm just going to take 9.8 times 1.5, multiply that together, take the square root, and see what I get. So when you do that, you should get the velocity is equal to 3.83 meters per second. Okay, let's go back to the question. It says they blah, 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 blah. What are the two disks' linear speeds when they reach the bottom of the ramp? Well, the solid disk is going 4.4 meters per second linearly, not how fast it's rotating, but how fast it's going in a straight line. And the hollow cylinder is going 3.83 meters per second in a straight line. So the question is, which one is faster and why? Well, if we look at it, the solid disk is going faster. Why is that? Why is it going faster? Well, the reason is because its moment of inertia is 1/2 mr squared, whereas this one is mr squared. Well, what does that mean to us? What it means is the solid disk is going faster because 1/2 mr squared, so it gets going faster. If it has a lower moment of inertia, it gets going faster. And once it gets going, it just keeps going. You know what I mean? Like nothing, this other one is not ever going to stop, catch up with it. If this one got the faster start, it's going to be winning the race, right? It goes faster and faster and faster and faster. So it's going to be the one who has the faster speed at the bottom. And that other one will never catch up. It really won't. It's going too slow. I mean, you know that from like a car race or a foot race. Like whoever's going to get that first initial start is going to go faster. All right, number 7 is going to go to an inclined plane. And we did inclined planes at the very beginning of the year, so we need to go back to thinking about those free body diagrams and thinking about how these are going to work. So if this is my sphere, my ball, well, it's a solid ball, so it's a sphere. It's going to have gravity. Gravity always acts straight down. It's going to have a normal force. The normal force always acts perpendicular to the base. And then it needs another force because what's going to make it roll? It's rolling without slipping. So do you remember what makes it roll without slipping? That is force of friction. And they give us the coefficient of friction, so that's another little hint there that that's what's going to be happening. Okay, number 1, or A, draw a diagram with forces acting on the sphere. Did that. Here we go. We've got the normal force, the force of friction, force of gravity. It says it's a 30-degree incline. We probably ought to include that here just so we remember what's going on here. Calculate the angular acceleration on the sphere. Okay, remember that, I'm going to try to make space here, that torque is equal to moment of inertia times acceleration. In this case, because it's a sphere, we're going to use 2/5 mr squared. That would be given to you. And we are looking for the angular acceleration, so I'm just going to use this formula, and I'm just going to start with that formula. So we have torque is equal to moment of inertia times angular acceleration. Torque, remember, what's the formula for torque? It's force times distance. Which force are we talking about? Well, we're talking about the force which is making it roll. That's what torque is. Torque is rolling. What force is making it roll? That's the force of friction that's making it roll. So the force of friction times the distance. In this case, the distance means the radius. Like we're talking about the ball rolling, so the distance is the radius. Okay, our inertia is 2/5 mr squared, and the acceleration is what we're looking for. Okay, well, remember I just said the distance is the same as the radius. It's the distance, the torque is just going around and around and around. So in this case, the distance is the radius, so that distance is going to cancel one of those radii. Okay, now that I've canceled those out, I also want to think about what is the force of friction. Well, here's my force of friction. How long is that vector? Well, the force of friction, remember, is mass times, let's write this over here. The force of friction is normal force times mu, or in other words, mu times mass times gravity. So we could plug that in there for that, but it is acting at a 30-degree angle. And so what we really have is we have cosine 30 times mu times mass times gravity is equal to 2/5 mr alpha. So now we have something else to cancel out, and that is the mass. So we can go ahead and cancel out that mass. And at this point, I think we probably just ought to plug stuff in and start working it out. Remember that your calculator should be in degree mode. And so when you plug it into degree mode, the cosine of 30 is 0.866. So when I plug this in, I have a 0.866 for the cosine 30. My mu is given as 0.2. My gravity, of course, is 9.8. So I've got those plugged in over here. My 2/5 stays there. Mass is gone. Radius is 0.2 meters. And then alpha is what I'm looking for. So again, I'm going to go to my calculator. I'm going to calculate this out and see what I get. So take a minute with your calculator and see what you get here. So when we plug that into our calculator, we get 21.2 radians per second squared. Remember, this is angular acceleration we're looking at, and that is measured in radians per second squared. So in this case, you're going to have an easy calculation, but let's think about what's going on. The linear acceleration of the outside of the sphere. So you have this sphere, and let's say you took a Sharpie and you made a mark on the outside of it. How fast is that as the linear acceleration? In other words, how fast is that Sharpie going around and around and around in the linear, like meters per second squared? So that's what we're looking at. To calculate that, remember that alpha is just the acceleration, linear acceleration over the radius. Or if we rearrange that, we would say that the linear acceleration is the alpha times the radius. And so we just figured out that our alpha is 21.2 radians per second squared, and our radius is equal to 0.2 meters. And if you wanted to say that's per 1 radian, to help you think about that conversion, that's our radius. And so now we just multiply this out. Our radians cancel with each other and then leave us with meters per second squared. We just have to put that into our calculator, and we get 4.24 meters per second squared. All right, we have one more concept in this section of notes on angular momentum. I'm going to stop this video here and make a separate video on the angular momentum.